All right, welcome back. We are Game 2005, that's game physics, at George Brown College. It's the fall 2020 semester, and it's week 5, part 1 of our broadcast. Today we're going to be talking about circular motion, as well as I want to talk about assignment 2. So we're going to start with assignment 2 in a second. Let's get to our schedule. So right now we're sitting at week 5. Looks like we got circular motion. Assignment 2 for our schedule should have been out last week, but again, we've been behind because I only gave you assignment 1 on week 3. So we're getting assignment 2 today, and it'll be due at the end of week 7, along with your midterm test. Notice that in the midterm, there is no planned lecture. I'm there to help you with your assignment 2, as well as if there's any midterm test issues, I'm there. So we'll use this time frame on week 7 as a study period or time for you to do your test. So that's coming up in 2 short weeks. The test will be true, false, multiple choice. You'll have a series of questions. It'll ask you to go through the material that we've been covering. Most of it is going to be calculations. You'll be having to answer some calculation type questions. So it'll be on the physics that covers everything from week 1 to week 6. That's what it's going to cover. You're going to have pretty much, I'm going to give you 1 minute per question, okay? And you'll have 2 attempts. That's how it'll work. So if I have a bunch of questions, let's say 60 questions, you'll have 60 minutes. That's how usually I do it. It won't take you 1 minute per question, but I want to give you enough time and at least a couple of attempts. It'll be a randomized multiple choice test that'll give you a chance to answer some of those physics questions. Practicing by doing your assignment and by looking at the examples that I present in class, it's going to help you do better on the test. I'm also going to present to you, which is as we approach week 6, I'll give you a cheat sheet that'll help you so that you don't have to look all over the place when you're live, to find all the formulas that are going to be relevant for my test. Not necessarily for physics, but just specifically for my test. I'm going to give you a cheat sheet that you're going to be able to use, every one of you. Okay, so that's coming up. And again, next week I'll probably give you that cheat sheet. So we're going to talk about assignment 2. But before we get there, I just wanted to share this video up on your Blackboard. So let's do that now that the video should be available on Blackboard. Yeah. And let's do this thing. Build content, YouTube video, and yep. Let's see if this thing works. It does. I figured it out. I figured out why the videos don't work sometimes when I'm doing this kind of thing. It has to do with my scheduling. If I schedule the video to happen at 11:10 and I try and put the video up here, and if it's 11:09, it's not going to appear. It's that simple. And I had to search it up to figure it out, but yeah, it was really dumb. So anyways, so now we're going to be fine doing that stuff every single time. We just have to wait for the appointed hour. Okay, so let's get back to this. So we're going to talk about the circular motion today, but first, what I really want to talk about, like I said, is the assignment 2 details. So let's get in there. So the assignment 2 details have been posted for you to see. They are in PDF format up on Blackboard. This assignment is due on week 7. That's Friday, October 23rd at midnight, and it's worth 10% of your final grade. All right, it's out of 100 points, just like the first assignment, and you will be doing 2 parts: the physics problem as well as the physics simulation portion. Notice the rubric at the bottom, or a division, if you will, of marks. 30% of your marks are for your physics problem, like you working it out on paper. 20% of your marks is the actual user interface for your physics simulation. This applies for your assignment number 1 as well, by the way, the same mark breakdown. And 35% for your actual functionality. So what if you're functional but it looks like crap? You'll lose 20%, guys. And I've seen some backgrounds that are inappropriate, images that don't make any sense. You're using my buttons and they stay next and back, and that makes no sense for your physics simulations. Anything like that takes away from your user interface and what it is, I want you to think about it as an application you're making that you're giving, let's say, to somebody else to do some physics calculations, if that app isn't usable or it looks like you slapped it together to satisfy my requirements, you will lose your 20% nice and easy. All right, so please make sure that your physics simulation user interface looks nice and makes sense to use. I've given you the ability to use IMGUI with the latest update to the SDL engine. You may or may not want to use it. It's totally up to you. You don't have to use IMGUI. You can make your own controls if you want, or you can just make use of buttons and labels. It's totally up to you, right? But it has to make sense. The more control that you give the user of your application that you're making, the better it is for you to test physics in your game. And this is what this thing is about. Okay, think about it as an experiment. You're actually testing how the physics work in the thing that I'm asking you to make. Okay, so what about this one? What is this one? Consider a metal loot crate at the top of a frictionless ramp. If the mass of the loot crate is 12.8 kilograms, then the ramp has a rise of 3 meters and a run of 4 meters. I know Star Wars, eh? It's just my thing. I don't know what maybe I don't know why it is, but I do this throughout. Compute the free body diagram of the loot crate at time 0. So in other words, when the loot crate is at the top of the ramp. Okay, so what is the free body diagram? What does that look like? Draw it out. You're going to need free body diagrams for your test. Chances are there might be one or more. Compute the net force and the acceleration of the loot crate at time 0. Given that the frictionless surface, what do we know about the acceleration as the object moves down the ramp? So what is the acceleration is what I'm asking here. Okay, how about this? Consider the loot crate as it leaves the ramp and moves onto a surface, it should say, onto a surface that now has some friction. Compute the free body diagram for this situation. If the coefficient of kinetic friction is 0.42, which is like steel on steel, calculate the new net force and the acceleration. So that's the next little bit of it. Okay? If we assume that the force of friction is constant after this point, how long will it take for the loot crate to stop moving, and at what distance in meters will the loot crate stop? Okay, so I want these details. Do this in a short document. Show me your work, your diagram, illustrating the problem and everything else. In your physics simulation, again, similar to what we talked about before, I want you to create some kind of elements to allow you to not just show the simulation, but give your user some options. For example, they should be able to change the width and the height of the ramp, the length and the height. They should be able to change the mass of the loot crate, change the coefficient of kinetic friction. Maybe it's not metal on metal. Maybe it's metal on rubber on metal. What does that look like? What if it's, but don't do frictionless because we've already done frictionless. Although you could turn down the friction if you want and show what that looks like. Update your display accordingly. So I've seen some user interfaces where people use checkboxes to turn options on and off. That's perfectly fine. Anything like that is good. Again, make it usable, make it good looking, right? The nicer you make this look, more points you're going to get. Be creative in your design, all right? Video demonstration's the same. I've had some questions around this. Again, all I'm looking for is a voiceover, all right? That's what I'm looking for the video demonstration. So you're going to demo your code functioning, show me that it works, right? Talk about it. Why did you make the design choices you made? Show me your work. So this is our calculation as an example. And you can have one person talk. Let's say a nice way to do it would be like one person to do the rough work, the calculations, another person to demo the functionality and maybe talk about the code. You can switch that up. If someone did it on assignment 1 and you want to switch up the partners for assignment 2, that's totally fine in terms of who does what. On that, if you're totally unhappy with your team, let's say, for example, you hate your team, you and your partner, you never want to work with this person again, or you're alone and you want to find someone to work with, please ping me on Discord and I'll rearrange the teams, all right? I'll remove people for this one. You don't have to work with the same people every single time, right? Maxim says, should it be like a console type application where you can enter some numbers? Because, for example, in my assignment 1, you change the speed distance by pressing the buttons to add or subtract from a current value, and my angle changes according to the mouse. No numbers entering. Is that fine? I mean, again, think about it as a usability exercise, Maxim. If you want to give it as much usability options as possible. So if I want to artificially change my angle, my throwing angle for the Wookiee, I should be able to do that. I think that should be something I do, not just the speed or I'm going to hit the stormtroopers every single time. What if I want to overshoot the stormtroopers or come close to the stormtroopers? I should be able to modify my numbers and give myself a sense of how your physics engine works. All right, when it comes to this kinetic, kinematic motion that you have going on. Okay. We have IM GUI sliders for that. Is that all right? Absolutely. Yeah, you don't want to make it look like Angry Birds. You want to make it so it's like an actual little app is what you want. So for your video, you want us to cover the math equation and the code functionality. Yes, I think you should just take a look at it. I mean, you should show it. Say, look, this is how we did our math. We use this formula. Here it is. Give me like a view of what that looks like. Again, it helps me look at what your thought process is, and it allows me to look at your work. If you don't include that, then I'm going to have to dig around to find that. And either you're going to have to submit that in its own document anyway, so you might as well show me the document, whether it's through a PowerPoint presentation slide where you slap on the document, the actual image, or you can show it to me separately. Okay, any other questions around assignments? Assignment 1 and assignment 2. So assignment 2, just to let you know again one more time, it has everything we had for assignment 1. It's a different problem, and it's using forces. Okay, it's not just using kinematic equations. For collisions, do we want the ball to bounce off the borders or just not to be able to move past it? Well, this really isn't a collision detection assignment, so it's really up to you. You can use AABB style collision detection at this point. It doesn't matter. That's not as important. That's for your effect. If you want to use radius type collision detection, you can do that too. It doesn't have to be accurate. It's more the movement I want to see than the collision detection at this point. Okay, so one thing to note, again, I just wanted to specify that when it's due, Friday, October 23rd, remember that your assignment 1 is due when? This Friday at midnight. So that means tomorrow night at midnight. You should be well into getting it done. If you're someone who is just starting it now, I would venture that you're not going to finish it on time. Okay, that's all I'm going to tell you. So please don't leave it to the last minute. There's a lot of detail here that I'm looking for, believe it or not, and it's going to take some time to get it done. Okay, so that is assignment number 2. Any questions before I move on? Any other questions? If you do have a question, put up your hand on the participants panel and I can stop. Otherwise, I'm going to move on. Okay, great. Thanks, guys. Let's move on. So today what we're going to be talking about is circular motion and other applications of Newton's laws. Oh, Eric has a question before we move on. Eric, talk to me. If you want to come on the mic. And I got a question from Maxim. Says, should I remake the app to make it more console-like? I can show after we finish the lecture. Sure, no problem, Maxim. Hang around and we'll do it. Eric, do you have a question? You don't want the thermal detonator to always hit the stormtrooper with changes to the speed, throw in other settings. Well, yeah, I mean, it'd be nice to do both, is what I'm saying. Give it as much latitude. Imagine that, you can lock on the stormtroopers. Imagine you testing your physics, your motion is what I'm looking for, and your calculations. I want to always hit the stormtroopers, no matter how much speed I put in. What is my angle going to have to be? That kind of stuff. You can also take it the other way. If I change my angle, how does my speed drop in order for me to hit the stormtroopers? Or maybe a check mark that says, we don't care if it hits the stormtroopers or not. I just want to modify, I want to freely, throw this thing at a specific speed and angle. The more options you present, Eric, the better. Because this is almost like a little tool that you're using, all right? That you're kind of calculating your trajectories. Okay, hopefully that gives you enough details. I need to move on now. I will take questions around assignments at the end of class. Let's continue. All right, so circular motion. Let's talk about what that is. So really, we've been talking about so far, everything has been linear. And now what we want to talk about is some kind of circular path. And a lot of times we deal with circular paths as well. Okay. Remember that motion is observed from an accelerating frame of reference. Okay, so that means, remember we talked about this, for force to be a thing, for there to be force, there must be acceleration. No acceleration, no force. All right, that's the way you should think about it when it comes to Newton's laws. Right, so there's always a need for acceleration. The other thing that we can talk about, Newton's laws also talks about motion of an object through a viscous medium. Viscosity, which means almost like a thickness or a fluid or something like that. Well, guess what? We live in a fluid ourselves. We live in an oxygenated, with nitrogen too, atmosphere. And the oxygen and nitrogen mix causes us to have friction. And the force of friction is a real thing. Wind force and all those kind of things. That's part of our viscous medium that we're talking about. So how does motion work when we move through that kind of medium? How is it affected? Is there resistance? What happens? So we're going to talk about that today. So one thing we want to talk about here is the idea of uniform circular motion. Okay, so a particle moves with a constant speed in a circular path with radius r, whatever that is, with a particular acceleration. We can say that the magnitude of the acceleration, so that means the length of the vector, if you think about it, is v squared over r. Okay, so v squared means the velocity squared over the radius, all right, or the speed over the radius in this case. The centripetal acceleration, or AC, C with the lowercase c, this is the subscript, centripetal acceleration is directed toward the center of the circle. And we kind of talked about that briefly last week. So when we're swinging something around, centripetal acceleration is always perpendicular to the velocity. So if my velocity vector, that usually is tangent to the curve, all right, tangent to the curve. So we're going to see that our velocity keeps on changing direction, right, as I move around the path. So my centripetal acceleration is always pointing towards the middle. If there's no change in speed and there's only a change in direction, then that is uniform circular motion. Okay. Here's an example of this. I have some kind of object, for example, that's tethered to the middle of, kind of to a center. And if I swing it around, swing it around, what happens? I can still apply force is equal to ma, right? And the way you do it is m is the mass of the object, a is the centripetal acceleration. And we know from the previous equation that centripetal acceleration is v squared over r. So we can just sub v squared over r. We're in the place of a. We sub it in, okay? And now we have a new equation for centripetal acceleration and force related to that, which is the sum of all forces is equal to the mass of the object times the velocity, v squared over r. Okay, that's what this is. So again, notice that there's a force that's directed towards the center, and that is what centripetal acceleration is, that force. Remember, force and acceleration go hand in hand. No force, no acceleration. No acceleration, no force. Okay, and I'm saying that for reasons. The other thing is that there is a tension that's created across a cable that goes from the center across the radius to where the object is, in this case a puck, that moves in a tangent to the circle. So notice that the angle, the vector that's happening, the direction of motion is always tangent to the circle, and it's being tethered by this wire, if you will, or this tension, this cable under tension the whole time. If the force, right, is greater than the tension, the tensile strength of the cable, the cable will break and the puck will break away from the path and leave the path, okay, in the direction that it was going, tangent to the curve when the cord broke. Okay, so that's what can happen. So, okay, that's an important consideration. So again, we're talking about the radial direction. The radial direction is this, right? Okay. So let's take a look at a case where we have a conical pendulum. Okay, so this is one case. I have a tether at the top, and what I'm doing is I'm swinging an object right below the tether. That is the conical pendulum. It makes a cone shape with its circular motion. That's what happens. So it undergoes uniform circular motion in the horizontal direction. So this way, okay? There is no motion up and down in the vertical direction. In fact, the vertical direction, we are in equilibrium. And you can see that. If I zoom in, you can see that the sum of all forces across the y-axis is 0, because this thing isn't bobbing up and down. It's just moving around in a circle, right? And we can say that if the sum of all forces across the y-axis is equal to 0, well then t cos theta, and notice that we're using cos for y this time and sine for x. This is reversed. We're normally not used to this kind of thing. We're normally used to cosine being associated with x, but there was 2 cases now that I've shown you that this is not the case. One is this conical circular motion, right? And as well as, actually it's going to apply to your assignment 2, which is when you have an item on a slope. If an item is on a slope, a particle on a slope actually reverses its association with sine and cosine along with its components. So for example, you're going to notice for anything on a slope, if there's a car on a slope or a loot crate in your case, you're going to see that x is associated with sine and y is associated with cosine. And it's a lot of times because of our frame of reference. Take a look at this angle that's happening with this tension, right? So you have a situation like this, right, where I have this this thing happen. But this here, the force of tension that's happening, right, can be broken down into its component forces. So we have t cos theta across the y-axis and t sine theta across the x-axis. So this is a componentized breakdown of the forces. And then again, multiplied, we kind of put theta in here relative to the angle. That's the theta, right? The relative angle of the wire relative to the y-axis. That's why it's reversed, right? In fact, if we think about this and if we rotate our reference frame so that this would be y and this would be x, then this makes sense. It makes sense why this is t cos theta, right? Because this would be the x-axis in most cases. The reason why we're using it like this is because this is the diagram. We have a tether, we have a conical pendulum, and so that's why the associations are reversed. When we move things around with algebra, we come down to this equation. Okay, I'm not going to prove this to you, but if you actually took these two equations and move them around, because we can make an association with one equation to the other, sine and cosine, then we get the L, right? Okay, which is the length of the cord, okay, times gravity, sine theta, tan theta, and you get the square root of that, and you can get the V, all right, or the speed. So that's an important consideration. So it's like one formula to do that for you, okay, in this conical pendulum example. In games, will we see conical pendulums very much? No, but you do see them in 3D sometimes, where you have some kind of motion that goes in a circle or something that spins out. Okay, so that's kind of something that that you might see. Let me just turn off Teams, because people just ping me regardless whether they see me as available or not. There we go. All right, so that is conical pendulum. Let's keep going. How about motion in a horizontal circle? Okay, so the speed at which the object moves depends on the mass of the object and the tension in the cord. The centripetal force is supplied by the tension. So the tension itself is actually like a normal force, and it kind of fires back at the middle, wherever I'm holding this object, okay? The maximum speed corresponds to the maximum tension. So these two things, maximum speed and maximum tension, as an example, are related, right? So the more tension I can handle, the more speed I can handle, which makes sense. So again, speed is equal to the square root of, again, if you notice, the tension times the radius over the mass. The heavier the mass, the bigger the object is relative to the tensile strength, then the lower the velocity, right? The smaller the mass and relative to the tensile strength, the higher the maximum velocity is, or the maximum speed. And what do we mean by motion in a horizontal circle? So imagine if I'm a slinger. I'm a slingshot person. I take I'm an old sling kind of person. I put a sling bullet inside of my slingshot, and I spin it over my head. As an example, the tension of the actual sling, right? That's why they make it pretty big. I can go as fast as I want, and what I want to do is I want to release one end of the sling to let my sling bullet leave at maximum velocity, which means if I go back up a couple slides, imagine if I'm in the middle and I'm looking at a top-down view of my circular motion. So I'm rotating my sling bullet or my sling over and over again, and I'm picking up speed as I'm going faster and faster. And the way it looks like, I have two ends of it, right? And then just as I'm ready to release it, right, I release one end of the sling, and the bullet is freed, and it leaves the circular motion with max speed. This was how we did it when it comes to using a sling bullet back in the day, right? We picked up speed. We used the circular motion of an object to increase its force. Why? I'm accelerating an object up to the point where it's at maximum speed, and then I'm letting it go, right? And it's going to go pretty fast. You can accelerate an object really, really good that way. All right, what about an object on a horizontal flat curve? What forces does it experience? Okay, well, here's the model of a car as a particle in uniform circular motion. So again, we know a couple things about this. One, we can see that the force of static friction is the thing that's keeping the car on the road, right? So again, rubber on concrete. If the tires of the car weren't made of rubber, and if they were made of, let's say, steel on concrete, the force of static friction may not be enough for the car to complete this curve nicely. It would keep going in a straight direction. Remember, by Newton's first laws, an object at rest tends to stay at rest. An object in motion tends to stay in the same direction of motion until I apply a force to it, right? If I can apply a force to it, that means an acceleration in a different direction, my object will change direction, which is what we're doing here with the curve, right? The road is actually applying a medium, or it's creating a medium for the car, right? Or it creates a friction so that the car has a tense, almost like an invisible, tension cable that goes from the car towards the center of the rotation, right? So the curve, notice this curve has a center, like way over here, right? And imagine the car's going around the curve, and the thing that's keeping the car in there is the force of static friction. So when we draw our free body diagram, then we draw the force of static friction towards the center of the rotation, the origin, if you will, of the rotation, right? So that's where the force of static friction goes towards, right? Then we have the normal force, which is pushing the car up. We know that the car is not going to sink into the ground, right? Typically, the car is not that heavy. The ground itself, or the road, is strong enough that the normal force is equal to mg, right? So that it can support the car, right? Knowing this, if I want to know the maximum speed of which a car can whip around a track, as an example, and by the way, this is relevant to games because we do make car games and other kind of movement games, we can say that the speed is equal to the square root of the coefficient of static friction times gr. Why gr? Because we know when we want to figure out the total force, we take the coefficient of static friction and multiply it by the normal force. And since the normal force is mg, and we want to also take into account the radius, right? The radius is going to give us a lowering or of energy, if you will, depending on how far how far on the curve the car is. Again, what that means is if I'm in the middle lane, right? Where do I feel more force? Closer to the middle or way out here? Where do you think? I want to see some check marks or a hand, maybe a hand that says, what do you think? Closer to the middle, do I feel more force here or do I feel more force there at the same speed? What do you think? Look at the equation. Okay, what does R mean? R means radius, right? So where would you feel more force? Further out, right? Some people say closer to the middle. Let's take a look at this. Well, what's the radius from here to here? It'd be greater, right? The greater the number, the greater the velocity. So that means the further out I am, the more force I'm going to experience, actually, the more velocity, right? The closer I am, it'll appear that I'm whipping around the track faster because I have a shorter distance to travel, right? But the reality is I'm going to apply for the same speed, to maintain the same speed or to maintain the same distance, I'm going to have a higher velocity on the outside, or higher speed on the outside because of this equation. All right, so that's what it does. That's how it works. That's how a car doesn't roll off into oblivion. And so this is why we make banked roads. We want to make banked roads so that way it'll help the coefficient of static friction so that the car doesn't blaze off into a bank somewhere, which is what we talk about here, a banked curve. So a banked curve is where the curve is not perfectly flat. So the normal doesn't go straight up and down. It actually goes at an angle. And the angle is towards the centripetal middle, if you will, the middle of the curve, the origin of the curved space. That's where the bank towards. You don't want to bank the other way. Banking over here on the outside is just going to make the car spin off faster. So what happens is this normal force actually starts pointing in the same direction as the force of static friction when you bank a curve, which means there's going to be more energy on this side than there is going this way, and it's going to help the car stay on the track, even in bad weather when my coefficient of static friction goes down because of slickness and because of snow. Okay? If that makes sense. Okay, so that's how this works. So the angle of the bank, if I want to find what the angle of the bank is to keep the car going at the same speed, given a particular force of static friction, right, then what is that? I can say v squared, so tan theta is equal to v squared over rg, and we can do an arctangent or atan2 on the computer to reverse engineer the angle and figure out what the best angle of the bank is. Okay? Okay, yeah, it is. It actually is in the driver's manual. Thank you very much. So the banking angle is independent of the mass of the vehicle. So it doesn't really matter how big the vehicle is or whatever. However, I want to point something else here that's not mentioned here. One thing that we haven't been talking about in any of this motion that we've been talking about is something called the center of mass. And the center of mass, what we're assuming that all objects we're modeling are particles still. Okay, the center of mass isn't higher up. This is why, objects like trucks, right, with a higher center of mass have the potential to roll over. The reason for this is because if there's the higher the center of mass is, so the higher up, the taller the object is, some part of its mass, or there's mass inside of it that's shifting around, the system that is the truck has mass that's shifting around, it can unbalance the truck, even superseding the bank curve and letting the truck roll over. So that's why, trucks, especially taller ones, aren't as great as navigating a curve, especially if it's a pretty big bank and at higher speeds than a lower down to the ground kind of vehicle. For example, a sports car has a much lower center of gravity, or call it a center of mass. The center of mass is actually quite low to the ground, which allows it to hug the ground more, and so that the coefficient of static friction that's being created the force of static friction that's being created between the ground and its tires are going to be more 1-to-1. The higher the value is, the taller the truck is or the car is, the less effective the coefficient of static friction is, because of the change of angle. All right, so keep that in mind when we talk about masses. We're thinking about that the center of mass is, we're modeling this whole thing as a particle still. So it's not 100% accurate. All right, but probably good enough for our games. All right, Ferris wheel example. So this is a Ferris wheel. We have a Ferris wheel. The normal and gravitational forces act in opposite directions. Why is that? Well, let's think about this idea. Again, we're talking about circular motion, but in this case, we have a mechanical circular motion that's happening. And when we think about a uniform circular motion, in this particular case, it's going to try and keep the object moving at the same pace. So imagine this is a gear of some kind or whatever. Well, here's a question for you. Would we have different forces at different places in time? When I have, let's say, a person inside of one of these little cars, is the person at the top, do they experience different forces than the person at the bottom? Here's a question. Does the person at the top feel lighter or heavier than the person at the bottom? What do you think? Lighter or heavier? It should be the same, Kara, but actually they feel lighter, like they're coming up out of their seat, especially if it's a uniform motion. Think about a roller coaster, which does that, right? As you come up on the roller coaster on a curve, you feel like you're going to leave your seat at the top of the motion, right? And that's why your shoulder straps and everything else keep you in, right? So you feel lighter at the top, and as you come down, you get the force, your vector, the vector of motion, right, as well as gravity is going in the same direction. That means there's twice as much force going down as you're coming down. So you're going to feel heavier at the bottom than you would at the top. Okay? Yeah, and that's how it works, right? Because, exactly, Cody, because what you want is, especially if it's tangent to the curve, like right here, if I drew a tangent line, let's draw a tangent line here by annotating. So imagine I'm at the top and I'm going this direction, right? This is the direction I'm going in. And then when I navigate this curve, I'm going to feel like I'm going to rise out of my chair until I get to this part where my tangent to the curve is this way, right? But at the top, right where I'm at the top end of the curve, the apex of motion, I'm going to feel like I'm going to come out of my chair a little bit. I'm going up in this direction. And then as I'm going to the bottom, right, notice that my motion is going to go down this way, right? It's going to keep moving, changing directions, right? And as you notice, if I come this way, right, as I'm going down towards the bottom, and if we're going to draw a free body diagram for this, the gravity is going to pull you down, and the angle of motion is going to pull you this way. Well, guess what? The resultant angle is somewhere in here, which is much longer than it would be if it was by itself, right? So if you were just like not moving at all, and if you just had velocity, it wouldn't matter, right? Let's try this again. Okay, so that is what this is. And let's continue. That's the Ferris wheel example. So the child is a particle. At the bottom of the loop, the upward force, the normal experienced by the object, is greater than its weight. Why is that? Well, because at the bottom of the loop, right, we have mass times gravity, but notice that the normal force is more because we have both things combined. I have a downward motion of the object plus I have gravity, right? Whereas when I'm at the top, there is less, those two motions kind of counteract each other, which creates the feeling of being lighter at the top. Because when you combine forces, right, there is less force in the downward direction. So because there's less force in the downward direction, we feel lighter. Okay? So this is the top of the circle, right? You can see the top. And these are two angles. Take a look at the equation. So this is the equation for the bottom. So the equation for the bottom is the normal force of the bottom minus mass times gravity, which is equal to mv squared over r. So that's that centrifugal acceleration equation, right? And then when we rearrange everything and we remove mass times gravity from this whole thing, we get mass times gravity times 1 plus v squared over rg. And that is the equation at the bottom. Now let's take a look at the equation at the top. So this is 1 plus, and this is something minus. Whenever we get something minus, we know that the top must be then, we'll get a normal force that is less at the top than there will be at the bottom. And the normal force is how we feel, because the normal force represents how much weight we feel, right? In fact, weight, which is mass times gravity, and so is normal force, mass times gravity is your apparent weight, if you will. It's equivalent to your apparent weight. Okay. So that is the roller coaster idea. All right, again, we can consider a ball moving in a circular path. This is vertical circular motion. So far we've talked about horizontal circular motion, which is, let's say, above my head, a conical pendulum, or something that is mechanical, right? And now we're talking about a vertical circular motion where we have non-uniform speeds. Why? Because as I'm going down the arc, if I have a down arc, like let's say if I'm spinning it with my hand, and on the down arc, the downside, if you will, I'm picking up speed down on the bottom and slowing down at the top. Why? Because the gravity and my motion are sometimes going in opposite directions, whereas at the bottom, they're going in the same direction, okay? And so we have a little equation for this. At the top, this is for vertical circular motion. T, the tensile strength, or the tension on the cable, right, is equal to mv squared over r minus mg. This is only for vertical circular motion that's non-uniform, guys. Non-uniform circular motion. It's not the same. The bottom is more than the top, as an example. Whereas the tension on the cable at the bottom is mv squared over r plus mg. So notice that we subtract it on the upward swing and we add it on the bottom swing. We can easily tell that the tension is more on the bottom. Tension meaning which is equal to mass times acceleration, right? If you think of what that is, right? Mass times acceleration. So the force is greater on the downward swing than it is on the upward swing. Okay? Again, this is just observations for you. You should understand this as just that. They're observations about what really happens. Okay? And gravity, in this case, still in the negative, or is it just a magnitude value? That's good. Well, it really depends on what the question is that you're trying to solve, Vincent. Right? How you frame the question, or how the question is framed to you, all depends on that's where the sign comes into play. Okay? If I'm looking at forces, then you want to make the sign negative, right? You want to, because forces are a vector, right? If I'm looking at something else, speeds, right? Speeds aren't a vector. Speed's a scalar. So we don't care about the direction of the speed, right? In that case, we don't care about if it's positive or negative. We care that it's positive. All right, the acceleration and force have tangential components. We talked about this. So if the force, the radial force that we're talking about here, here's the radial force. And this is in non-uniform circular motion now, okay? Not uniform. We talk radial force when we talk non-uniform circular motion, right? Centripetal force is usually used for when we discuss things like uniform circular motion. But radial force is the stuff that we're talking about when we're talking non-uniform circular motion. So you can see that the sum of all forces then is equal to this radial force, which is the sum of all the radial forces going towards the center of the circle, right? Plus the sum of all forces tangential to the curve, right? That gives us a new vector for where this thing is going to go. So for example, in this case, the angle is going up this way, right? Here is the force tangent to the curve. Here is the forces that are radial towards the middle of the curve, and this is the resultant forces when you add these two vectors together. Okay? And so if that's true, right, and one thing that we're missing here, if this is non-uniform circular motion, we don't have gravity. If this was like on the downward swing, you can see that there would be gravity here as well. That would also be another force that would change the angle of this particular motion in another direction. All right. So this, again, vertical circle with non-uniform speed. We can talk about how this works. You can see here when we talk about at the top of the circle, right, we have which is very similar to what we did with the Ferris wheel example. We have the mass times gravity pulling down, the same mass times gravity here. We have at the top, as an example, we have the tension at the top pulling towards the middle of the circular motion, right? And you can see that the tension is lower because, again, we talked about that normal force. the normal force is lower at the top than it is at the bottom, and since normal force is usually equal to the tension that goes towards the middle, this amount is lower, right? So we feel like there's less forces at the top than there are at the bottom, right? Whereas, as we swing back to the bottom, we can see that the amount of tension at the bottom increases because we have numbers that are working together to increase the force that's going in a downward direction. And therefore, to counteract that force, the tensile strength of the rope has to be very high compared to the tensile strength at the top of the motion. Whew. So this is how we can use this equation. The tension at any point can be found by T is equal to mass times gravity, and then all times v squared over rg plus cos theta. And notice how cos is being used top and bottom. Again, this is another example of component, relational reversal, right? Normally I relate something that's up and down with sine, but now I'm relating it to cosine. Why? Because of this angle. This angle here, where we are rotating our frame of reference to match the angle that we're coming down at, where the top of the frame of reference, normally this would be the y-axis, right, is pointing to the middle, and this would be the x-axis. So because of this, we can see that this thing would be reversed, because since we're changing our frame of reference, because we're rotating everything. Okay, top and bottom of the circle, we can split it off, and we want to find the tension at the bottom. Here's the tension at the bottom. Did I miss something? Nope. And here's the tension at the top. So we can break these equations, and notice they're very similar to what we've seen before. So we add something at the bottom, we subtract something at the top, because there's the apparent weight at the top is less in this non-uniform circular motion. All right. That is a lot of what we need for game development, because we want to sometimes whip around a corner, or we want to, we want to have the person experience what it's like, especially in a racing kind of game, or in any kind of motion that's following a path. If you want realistic, kind of motion, and for the driver to have to compensate, as an example, for the curve, then we use these equations. And what I mean by compensating is it becomes more difficult. One of the things we do, why our cars have a driving, like a wheel at all, is not just to change directions, but we can also use it to compensate for the curve itself. When our front wheels and our steering wheel change direction, it actually increases the coefficient of static friction in one direction, so that way our car hugs the road a little bit more, right? If the wheel is going straight, then what's going to happen is, if I don't follow the road, if the angle of my tires aren't following the angle of the path or the angle tangent to the curve, I'm going to fly off the curve, chances are, right? The direction of my front tires really help me to stay on the road. And the tension that I would feel in a simulation would be greater as I whip around the curve faster. At the same time, if I'm on some kind of pendulum, or if I'm on some kind of roller coaster, if I'm simulating that, and normally we don't do that with games, this is where this kind of circular motion comes into play. Okay. Motion in accelerated frames, they talk about this something called the fictitious force from the accelerated frame of reference. This is fantastic information, but it makes no sense for you guys unless you're doing VR, right? Where we have something called the centrifugal force, almost like being in a centrifuge, where you feel like a fictitious force that's pressing you outside, towards the outside part of your frame of reference. What does this mean? It means when you're traveling inside of a car, you don't feel like you're accelerating. You feel like you're sitting in place, right? So your frame of reference is related to the car. It's almost like you're a child of the car object. So you're moving along, your coordinate frame, if you will, is moving along at the same pace as the car, right? So what happens is, since you're inside the car, and if we suggest that you're not a particle, and let's say you're not 100% tied to the car, you will feel a fictitious force inside of the container of the car towards the outside of the circle, pointing away, and that's centrifugal force. As you feel drawn outside of the car. If you actually were to open the door of the car on the outside swing, you may feel a pull or a desire to fall out of the car. By the way, this happened to me in real life. I was in a car, my door wasn't closed, right? We're on a highway and we're going around the curve about 80 kilometers an hour. My dad felt it was the need to, to kind of whip around the curve. And as he did so, it had enough velocity from my car door to whip open, right? This is a real story. And at the time, back in the day, we're talking about, I'm dating myself now, there were no seatbelt laws whatsoever. That's how far back we're talking about now. I was quite a little guy, right? Let me tell you that I saw my life flash in my eyes as I literally hung onto the door with one arm and my legs were inside the car and my other arm was holding myself in. If a little bit longer and there would be no Tom and we wouldn't be having this conversation. I would have been flung out into space, right? But that fictitious force was quite real to me, right? And your game object, you could make it feel that way if you're gonna produce that kind of game. Chances are, though, I'm gonna pass this thing because for the most part, we don't have this kind of stuff in games unless you're playing ultra realistic simulation, some kind of VR game where you want to have a rumble effect or feedback effect, or you're playing a racing car game. Okay, and why? Because remember, Newton's first law, a particle in motion tends to stay in motion in the same direction. I think that's the most important part, unless I apply forces to it. Newton's first law, right? So I want to try and go outside the car, but the car is holding me in. The container of the car is making me stay inside my reference frame. And there's other forces here. The apparent force, this Coriolis force, right? It is also created, and it's really nice, and it's a beautiful thing, but it really doesn't apply to us for game development. I'm putting it out here because there's other circular forces that we will not be focusing on this semester. Okay? All right, let's get into our examples for today. So let's talk about this again. So here's the conical pendulum question. Guys, why am I giving you conical pendulum examples? Because there's on your test, there's going to be questions that are eerily similar to this example, right? So please study it. If you study the conical pendulum example, then you'll be quickly able to answer the questions as opposed to searching around for answers on how to do it, okay? So let's take a look. So it says a small ball of mass m is suspended, right, from a string of length L. Okay, this is how you normally get it. The ball revolves with constant speed. So once we see constant speed, in my mind I'm thinking uniform circular motion, right? Constant speed v in a horizontal circle of radius r. So this is the radius here. This is the length of the string here, as it's tethered to the ceiling in this case, right? Because the string sweeps out the surface of a cone to the system, it is known as a conical pendulum because it's sweeping out the motion. That's what it's doing. Okay. Conceptualize. Imagine the motion of the ball and convince yourself that the circle sweeps at a cone. All right. Categorize. The ball in figure 6.3 does not accelerate vertically. It doesn't go up and down. It's only sweeping around horizontally. And so the particle up and down is in vertical equilibrium, right? The only time where we have forces changing is in this circular path, tangential to the curve. Okay? And here are the equations. We apply the particle in equilibrium model in the vertical direction. So vertically, we have the particle in equilibrium. The component on the y-axis, the sum of all forces on the y-axis, is equal to the tension, right, along the cable, cos theta minus this force of gravity, right, times mass. So that's this. And notice I'm just going to put it as equation 1, t cos theta is equal to mg. Equation 2 is the sum of all forces across the x-axis. Now we're experiencing force. We know that. we take t sine theta is equal to mass times the centripetal acceleration. Remember, we use centripetal acceleration when we have uniform circular motion. And we replace AC with mv squared over r, so that we get t sine theta is equal to mv squared over r. With some algebraic manipulation, we know we can find out the angle. We can reverse engineer the angle by getting the arc tangent of v squared over rg. And that would give us the angle, whatever that would be. For the velocity, or for the speed, we take the square root of rg tan theta, right? If we wanted to find the speed. Okay, and we can also incorporate, if we've been given this information, the length of the cable, right? The length of the cable give us more information. And sometimes we don't have, as an example, the radius, but we have the length of the cable that's been given to us. Okay. So that is the way we would figure this equation out, by applying those equations. We just sub in the values that we know. Okay, here's the next one. How fast can a can spin? This is another type of question you might get. A puck of mass 0.5 kilograms is attached to the end of a cord 1.5 meters long. So this is the information we have. These are the variables. The puck moves in a horizontal circle as shown in figure 6.1. Okay, so there we go. So this goes in this direction. This is a top-down view, horizontal circle, right? Okay, if the cord can withstand a maximum tension of 50 newtons, what is the maximum speed at which the puck can move before the cord breaks? Assume the string remains horizontal during the entire motion, so it's not jumping around. Okay? If that's true, and if the puck stays at the ground level the entire time, and we assume that the center of mass is kind of lower down to the puck, we can eliminate all upward movement, which is what we want to do in this case, right? Notice that the force, right? And this is force radial this time, moving towards the middle. It's like centripetal force, but it's moving towards the middle of the circle, right? And notice it says, here's the radius, right? So how do I figure this out? It says it makes sense that the stronger the cord, the faster the puck can move around the cord before it breaks. Also, we expect a more massive puck to break the cord at lower speed, right? So that makes sense. Categorize. Because the puck moves in a circular path, we model it as a particle in uniform circular motion. Why? Because it's not changing, right, around this axis. Again, looking at this as a top-down view. Okay? And so we use our equations. The tension, again, anytime we look at tension, it's the idea of F is equal to ma. This is not just tension. We always think about this as the force of tension. The force of tension, this is sometimes where people get confused. How do we get this? How do we derive this? The force of tension is equal to mass times acceleration. Here we're looking at the centripetal acceleration again, v squared over r, where we have v, the speed, is equal to square root of the tension times r over m. That is the way we solve for v, right? Now what about the maximum tension, the maximum speed based on some information we have, right? If this is our general equation for speed, then V max is we want to get the maximum amount of tension. So we say that if our maximum amount of tension is 50 newtons, which is what we've been given, we multiply it by the radius, 1.5 meters, divide it by the mass, right? And we're going to get, if we take the square root of that, we know that the maximum speed will be 12.2 meters per second. Okay? So we first find out the equation, put it in the right form, then sub in the values that we know, and then we'll have the answer for this particular problem. Okay? All right. What is the maximum speed of the car? Here's another one that you might see. Okay? Oops. So zoom in here. So again, a 1,500 kilogram car moving on a flat horizontal road, right? Negotiates a curve as shown in figure 6.4. Here it is. If the radius of the curve is 35 meters, radius from here to the middle, right? And the coefficient of static friction between the tires and the dry pavement is 0.523. So tires being rubber, dry pavement. find the maximum speed of the car can have and still make the turn successfully. So again, we imagine that the curved roadway is part of a large circle, so the car is moving in a circle. Based on the conceptualized step, right, we model the car as a particle in uniform motion, right, because it's not moving up and down, and it's not slowing down or speeding up, right? When we analyze this one, we draw a free body diagram to figure out where all the forces are, and we notice that the force of static friction is pointing to the middle of the curve, where the normal force in this case is going up, and it's counteracting the force of gravity, right, based on the mass of the vehicle. Okay, so we can say that the maximum speed, or Vmax, the car can have around the curve is the speed at which it is on the verge of skidding outward. At this point, the friction force has its maximum value, so friction static max, which is equal to mu, so the coefficient of static friction times the normal force. That's why we need this diagram, because we've got to figure that this normal force is what we need to calculate the total force, right? The total tension that we can have, if you will, across the road as we're moving forward, right? Which is really what we're doing at the end of the day. So when we sit there and we calculate it, we can say that the maximum force of static friction is equal to the coefficient of static friction times the normal force. So, and what we do, the normal force is mg, g being gravity, right? And we want to multiply it by v squared over r, because we also know that force is equal to mass times acceleration. And we know we can convert mass times acceleration to mass times v squared over r. So we can have a relationship between mu static, normal force, and mass. We have all these things in there. When we rebalance the equation, we know that the sum of all forces across the y-axis is equal to mg, right? N is equal to mg. Normal force is equal to mg. It's in balance. It's in equilibrium, right? Whereas we know the other forces, we can use the equation that Vmax, just like we did earlier, is equal to the square root of the normal force, and normal force times radius over the mass, which is what this is. Normal force times the coefficient of static friction, right, times radius over the mass, right? And when we substitute normal force for mg, then we have mass over at mass. We can cancel out the mass, right? And all we care at the end is the coefficient of static friction times gravity times the radius. Take that, the square root of that, and that is our maximum velocity, or our maximum speed. Why? Mass is irrelevant. Mass is irrelevant for this equation. It cancels out because of this relationship. Thanks, Kiara. When we sub in our values we substitute mu, 0.523. By the way, in Greek we call it mu, but mu for science and physics. 9.8 meters per second for the force of gravity on Earth, closer to the ground. 35 meters is the radius, right? We sub in all the values we know. And then we're left with, when we take the square root of those values, 13.4 meters per second is the velocity, or the speed maximum, as we whip around the curve. 13.4 meters per second. By the way, what does that work out to in kilometers per hour? You're going to have to do some of these conversions. So if I take, as an example, 13.4 meters per second, right? 13.4 every second. I multiply that by 60, right? That means it's 804 meters per minute. 800 meters per minute, right? And if you multiply that by 60 again, right, you're going to get 48,000 meters per hour, right? Divide that by 1,000 meters, it's 48 kilometers an hour. That's what this means. This curve can nicely be navigated based on the coefficient of static friction, the gravity, and the radius of the actual curve, 48 kilometers per hour before this car spins off into oblivion, based on the stats we've been given. We don't care about the mass of the car. And the question I have for you when you look at this number is, does it make sense? Always think about, does it make sense? It's 48 kilometers an hour. Does that make sense, for most roadways? And the answer in your mind should be no. But then, if you think about it, it does make sense because all of our roadways, our curves to go back on the on-ramp or down-ramp are banked. And the banked roadway is going to make a difference here in terms of their maximum speed. Okay. Let's continue. All right. The Ferris wheel problem, you may see something that looks like this. A child of mass m rides on the Ferris wheel as shown, right? The child moves in a vertical circle, radius 10 meters, at a constant speed of 3 meters per second. Okay. We're just given that this is a constant speed. Why? It's mechanical vertical motion. Okay? It's uniform vertical motion, right? Why? Because it's mechanical. If this was an arm whipping around the child, right? If I somehow was a giant and I had the child was like at the end of my rope or something like that, this would not be uniform circular motion. But because it's a machine, it's mechanical circular motion. This mechanical circular motion is uniform on the vertical. However, the child will experience changes in weight, apparent changes in weight or fictitious forces, right, at the top and at the bottom. Okay, we've kind of covered this already, but it covers the math here a little bit in terms of the way it works. And we can sub in the values to kind of give us a sense of the substitute the numeric value. When the question is asked is, determine the force exerted by the seat on the child at the bottom of the ride. Express your answer in terms of the weight of the child, mg. In other words, express your answer in g's. How many g's? How many gravities does the child feel? All right. This actually would work well with a fighter jet too. At the bottom of the dive of a fighter jet, the person who's in the fighter pilot, I'll be okay. The fighter pilot feels a higher amount of G-force as at the bottom of the the dive, as an example, compared to at the top. At the top, right? It really depends again on the amount on the climb. There's less weight on the climb. However, what you will get is weird centripetal acceleration depending on the curve of the jet, right, as it's moving. Okay, so that's where people can block out and all this kind of stuff because your center of gravity is thrown off and you're under a lot of strain in terms of a bunch of masses of gravity that are thrown at you. I don't know what the average blackout point is, but I think it goes to like, is it 10 Gs? I can't remember. It's something crazy. We can look it up. But anyways, this is what they're saying. How many Gs, if you think about this? How many Gs? Not masses, but how many gravities, if you will. So it's like I'm saying at the bottom, the child will have 1.09 Gs. So 9% greater feel of gravity at the bottom. He feels 9% heavier at the bottom than he would at the top. Okay. And at the top, they would feel 90% of mass. So again, the opposite of what we feel kind of at the bottom to some degree. Okay, so these are the two equations here. I'm not going to go through them because chances are you may not see a question like this on the test. All right, keep your eye on the ball. A small sphere of mass m is attached to the end of a cord of length r. Okay, cool. And set into motion in a vertical circle about a fixed point O, as illustrated in figure 6.9. All right. Determine the tangential acceleration of the sphere and the tension in the cord at any instant when the speed of the sphere is v and the cord makes an angle theta with the vertical. This is an example of non-uniform circular motion. It's vertical motion. It's not machine-based. Right, as an example, we are tethered, but the motion is going to be non-uniform. And because it's non-uniform, we use other equations for this. These equations, okay? And all we do here is, again, we just sub in those equations. I'm just trying to help you identify as I go to the next one. Here's some homework for you, all right? Homework for the next time. you will get a problem that might look like this, right, with different numbers. Okay, you will get a problem. A light string can support a stationary hanging load of 25 kilograms before breaking, this light string. Okay, so I'm giving you some properties of the string. 25 kilograms. What does that mean in terms of the force of tension? What's the force of tension that this string can support then? If the light string can support this hanging load, what does this mean to the, what is the force that I'm talking about here? How do I calculate that? If I know the kilograms, right, then how do I know to calculate the maximum force in the string? Well, there's some hints here. One is hanging load. Hanging load means that when I apply gravity to it, to the mass, right, it's not going to break. Before breaking, just before breaking, that is my maximum load, 25 kilograms. So if I take that, 25 kilograms, because force is equal to MA, right, and I take 25 kilograms and multiply it by 9.8, right, then the maximum force that I can experience on this string is 245 newtons. Okay. An object of mass M, 3 kilograms, attached to the string rotates on a frictionless table. Okay. It's horizontal table. In a circle of radius R is equal to 0.8 meters. And the other end of the string is held fixed, as in figure 6.1. Like this. What range of speeds can the object have before the string breaks? Range of speeds. What's the maximum speed is what this is saying. Okay. I know that this is the maximum tension, right? Tension is equal to force, right? Force is equal to mass times acceleration. I know the force, 245 is the force. I can figure out acceleration. If I know acceleration, I can figure out, the maximum speed. We know this already. We've done this similar thing to this one with the puck on ice. Okay? We can apply the same things here. Problem 2. A curve in a road forms a part of a horizontal circle. Okay, same thing as a curve in the road. We're given a couple things. It goes around at a constant speed of 14 meters per second, and the total horizontal force in the driver has a magnitude of 130 newtons. Okay? What is the total horizontal force in the driver if the speed on the same curve is 18 meters per second instead? So I have this relationship, and I'm looking for to get another relationship based on the new speed. This is a good problem, right? So what happens? How much more force, right, kind of is applied on the driver? What does the driver feel as they're going around? Imagine the driver is the particle that's being tethered, a particle in motion. Again, this is uniform circular motion because we're talking about a curve in a road, right, and a horizontal circle. These are keys. Okay. Consider a conical pendulum. Again, we're talking about uniform circular motion. Problem 4. Okay, this is something you may see. Here's your roller coaster. I know Cody was mentioning it, right? You have a roller coaster, you go down, right? And as you're going down, it's like you're at the bottom of a circle, yeah? And then you're going up, and as you're going up, you're at the top of a circle. And the circle could be different depending on the curve in the roller coaster, right? So it says the path of the coaster is in its initial point shown in figure to point 2B, all right? Path of the coaster from its initial point shown in the figure to point B involves only up and down motion as seen by the riders, with no motion to the left or right. So in other words, your car isn't, vibrating. We're assuming there's no vibration or motion left and right. Your car is, kind of moving in a straight line, in a straight direction. Okay? So there's no Z forces in this case, only X and Y. If we're looking at X and Y, Y being this way, X being this way, but there's no Z, is what it's saying. Okay? What is the maximum speed of the vehicle? The vehicle can have a point B, right, and still remain on the track. So if the vehicle is not tethered, let's say, by the roller coaster itself, it's not being held in place. It just is going to be being held in by, you know, the weight of the vehicle itself, right? Because we're giving 500 kilograms to the vehicle, right? The car, and we're given the radius, right? So we know what the R1 is and what R2 is. R1 is 10 meters and R2 is 15 meters, right? So how do I figure this one out? Well, curious, is it uniform circular motion or is it non-uniform circular motion for this one? What do you think? Uniform or non-uniform? Okay, non-uniform. That's good. Why? Because it's like a roller coaster. Sorry, it's like a pendulum in some ways, but or a vertical motion that's tethered in some ways, right? That's what's happening. And so we're going to have more speed at the bottom, which means it's not uniform, and less speed at the top, non-uniform, right? If the speed was the same at the bottom as at the top, it would be uniform. Uniform motion, meaning uniform speed. Also, another way to know that this is true is at the bottom the radius is smaller, and at the top it's bigger. Right there, you know that how the speed will be affected at different points in time. This is a more complex problem. It's a multi-part problem that you'd figure out, and you'd break it down in terms of two different piece parts: part A and part B. Part A is if the vehicle has a speed of 20 meters at point A, what is the force exerted by the track on the car at this point? Right here. Right? And B, what is the maximum speed that the vehicle can have at point B when it climbs up to here and still remain on the track? So there's two different parts, a multi-part question. You might get one of these. I think I built one or two of these for the midterm test. All right, and those are the things I'd like you to study for this week. After this, I'm really available for questions. I'm going to stop recording now. This is everything I wanted to talk to you today about circular motion, and I'm going to move on to questions about assignment 1 and about assignment 2. I'm going to stop recording now.